For most of human history, empty space felt like one of the simplest ideas imaginable. It was the absence of things. Where there was no matter, no air, no dust, no light, there was nothing. Physics inherited that intuition almost intact. Even today, when people hear the word vacuum, they imagine a perfect void, a silent, inert backdrop in which real objects move. Yet modern cosmology and quantum field theory have forced us to confront an uncomfortable truth. The closer we look at emptiness, the more structure we find. And the more carefully we define nothing, the less it resembles nothing at all. The most familiar doorway into this confusion is the atom. You have likely heard the statement many times: atoms are almost entirely empty space. If you magnify an atom to the size of a cathedral, the nucleus would be smaller than a grain of sand suspended at the center, while the electrons would occupy a vast surrounding region. By volume, more than 99.999% of the atom is empty. Push this idea further, and it becomes almost absurd. If all the empty space inside human atoms were removed, compressing only the remaining nuclei together, the entire human species could fit into something roughly the size of a sugar cube. The numbers are not controversial. They are straightforward consequences of atomic dimensions measured in laboratories. And yet this picture collides violently with everyday experience. If atoms are almost entirely empty, why does your hand not pass effortlessly through a wall? Why does a table feel solid? Why does the floor stop you instead of yielding like fog? The naive answer is often that electrons repel each other, which is true but incomplete. That explanation still sneaks in a classical picture of tiny, hard particles pushing one another like microscopic billiard balls. What actually prevents interpenetration is not solidity in the classical sense, but the structure of quantum fields and the rules governing their allowed states. The resistance you feel when you press on a wall is not the sensation of matter being tightly packed. It is the manifestation of electromagnetic fields enforcing quantum constraints on how electrons may occupy space and energy levels. What feels solid is not dense matter, but stable field configurations that strongly resist rearrangement. This is the first crack in the classical idea of emptiness. Even regions that appear empty of particles are not empty of influence. They are filled with fields, and those fields determine what is allowed to happen and what is forbidden. In classical physics, however, the story stopped there. Fields existed, but they could be quiet. Remove charges, currents, and radiation, and the electromagnetic field could settle into a trivial zero-energy state. A classical vacuum was a peaceful place, no matter, no energy, no dynamics. It was the natural baseline of reality. Quantum physics erased that baseline. In quantum theory, nothing is no longer synonymous with zero. A vacuum is not defined as the absence of everything, but as the lowest energy state of a system. That distinction seems small, but its consequences are enormous. In quantum mechanics, even the lowest energy state cannot be completely still. The uncertainty principle forbids perfect rest. For any system that can be described as an oscillator, and quantum fields can be decomposed into infinitely many oscillators, the lowest allowed energy is not zero, but a finite residual value. This is called zero-point energy. It is not energy you can remove, and it is not energy you can turn off. It is built into the structure of the theory. When this logic is applied to quantum fields, the result is radical. Every point in space is associated with quantum fields. Each field has modes of oscillation, and each mode carries a minimum irreducible energy even in its ground state. The quantum vacuum, then, is not an inert void, but a restless ground state filled with fluctuations that never completely vanish. It is not empty in the everyday sense. It is empty only of real, long-lived particles. Beneath that surface, the fields are alive with activity. A common metaphor is that of a boiling soup, but even that is misleading if taken too literally. Nothing is sloshing around in a classical fluid sense. What fluctuates are the values of fields themselves varying in time and space according to quantum rules. These fluctuations are extremely small and extremely fast, but they are not optional. They are required by the structure of quantum theory. Maintaining a perfectly classical vacuum, a region of space with exactly zero energy, zero fluctuations, zero fields, would actually require infinite control and infinite energy. In that sense, nothingness is not the default state of nature. It is an unstable idealization that reality refuses to occupy. This abstract claim becomes more concrete when we turn to numerical simulations. One of the most striking visualizations of quantum emptiness comes from lattice quantum chromodynamics, particularly the work of physicist Derek Lineweber and collaborators. Using supercomputers, they simulate the behavior of the gluon field, the field responsible for binding quarks inside protons and neutrons. When these simulations are rendered visually, the vacuum does not appear smooth or featureless. Instead, it is filled with rapidly changing regions of positive and negative field intensity, often represented in red and blue. These structures emerge and vanish on timescales as short as 10 to the power of -24 seconds. They are not particles in the conventional sense, but neither are they nothing. They are manifestations of the vacuum structure of the gluon field itself. What these images reveal is not chaos, but constraint. The vacuum is structured because the underlying fields obey equations, symmetries, and conservation laws. The apparent turbulence is a reflection of quantum uncertainty, acting on fields with self-interactions. Even when no quarks are present, the gluon field does not flatten into silence. Its ground state is dynamic. The emptiness between particles carries information about the theory that governs them. At this point, it becomes clear that the word nothing is doing far too much work. In classical language, nothingness means the absence of entities. In quantum field theory, it means the lowest energy configuration of a set of fields that exist everywhere. Those fields do not disappear when particles are removed. They remain and they fluctuate. The vacuum is not an empty stage. It is the stage itself, constantly active, even when no actors are present. This realization forces a profound shift in how we understand matter. In the quantum field picture, particles are not fundamental building blocks in the old sense. They are excitations of fields. An electron is not a tiny object moving through empty space. It is a localized excitation of the electron field. A photon is an excitation of the electromagnetic field. A quark is an excitation of a quark field, interacting with the gluon field that fills space around it. When a particle is annihilated, the field does not vanish. It simply relaxes back toward its ground state. The ocean remains, even when the wave passes. Seen from this perspective, the solidity of matter is no longer mysterious. What you experience as a solid object is a stable pattern of interacting fields locked into place by quantum rules and conservation laws. The resistance you feel is not the collision of hard pieces of matter, but the energetic cost of disturbing those patterns. To push your hand through a wall would require rearranging electromagnetic and quantum states in ways that demand enormous energy. The emptiness between atoms is not permissive emptiness. It is structured emptiness, governed by fields that enforce strict constraints. This also reframes the question of what you are made of. If matter is not fundamentally solid, then neither are you. Your body is not a collection of tiny hard things packed together in space. It is a long-lived excitation of multiple quantum fields, organized into atoms, molecules, cells, and tissues by layers of physical law. Your mass is not simply the sum of particle masses. Much of it arises from energy stored in fields and interactions. Your stability is not due to material rigidity, but to dynamical balance. In this sense, the statement that you are made of empty space is both true and deeply misleading. You are not made of emptiness, in the classical sense of absence. You are made of fields, and those fields exist everywhere, including in regions we once called empty. The vacuum is not the opposite of matter. It is the medium from which matter emerges as excitation and pattern. The illusion of emptiness survives only as long as we insist on classical intuition in a quantum world. Once we abandon the idea that reality must be built from solid pieces moving through a void, a different picture comes into focus. Space itself is physical. Its lowest energy state is active. And what we call matter is not something placed into that space, but something that arises from it. The equations of modern physics treat fields as primary and particles as secondary. They predict fluctuations even in perfect vacuums. They are confirmed by simulations and experiments. Emptiness, in the deepest physical sense, is not empty at all. And once that idea is accepted, a more unsettling conclusion follows. You are not standing in a universe made of solid things separated by nothing. You are a temporary, organized vibration in a continuous sea of energy and fields. The wall, the floor, the air, and your own body are all different expressions of the same underlying structure. The illusion was never that atoms were empty. The illusion was that emptiness meant absence. For centuries, physics was built on a quiet assumption that almost no one questioned space itself was passive. It was a container, a neutral stage on which matter moved and forces acted. In the worldview inherited from Isaac Newton, space and time existed independently of the objects within them. Forces acted instantaneously across distance, as if objects could reach out and influence one another through empty nothingness. Gravity pulled charges, attracted or repelled, but the space between them remained mute. It carried no substance, no memory, no dynamics of its own. It was simply there. This picture worked astonishingly well for predicting motion. Planets followed their orbits, projectiles traced clean arcs, tides rose and fell. And because it worked, it shaped intuition. Matter felt primary. Space felt secondary. If you removed all objects, what remained was an empty box, perfectly silent, perfectly inert. The first deep fracture in this worldview did not come from mathematics, but from careful observation and stubborn imagination. Michael Faraday, a largely self-taught experimentalist, began to suspect that forces did not leap magically across emptiness. When he sprinkled iron filings around a magnet, he did not see random motion. He saw structure. The filings traced graceful arcs, revealing patterns that seemed to belong to space itself. Faraday introduced a radical idea, perhaps. Forces were not mysterious actions at a distance, but the result of something real filling the space between objects. He called them fields. Faraday's lines of force were initially dismissed by many as visual aids, not physical entities. But Faraday took them seriously. To him, the magnetic field was not a bookkeeping trick. It was a physical condition of space, altered by the presence of magnets and charges capable of storing energy and exerting influence. When an electric charge moved, it disturbed the field around it, and that disturbance could propagate outward. Suddenly, space was no longer empty. It had properties. It could be stretched, twisted, energized. This shift was subtle, but profound. Space was no longer just where physics happened. Space itself was participating. Later, James Clerk Maxwell translated Faraday's intuition into equations, showing that electric and magnetic fields were deeply linked and could propagate as waves. Light itself emerged as a traveling disturbance of the electromagnetic field. This was a turning point. Light was no longer a stream of tiny particles flying through emptiness. It was something the field was doing. Space filled with fields had become active. Yet even then, fields were still often treated as secondary. Matter generated fields. Fields mediated forces. But matter remained the real stuff. That hierarchy survived into the early days of quantum mechanics, where electrons and photons were introduced as discrete particles, with strange wave-like properties. The language shifted, but the intuition lagged behind. Quantum field theory completed the reversal. In QFT, fields are not optional additions layered on top of particles. Fields are the fundamental entities. Every type of elementary particle corresponds to its own field extending throughout all of space. The electron field is everywhere. The quark fields are everywhere. The electromagnetic field is everywhere. Even in regions devoid of particles, the fields remain. They define what is possible. One way to approach this idea is to abandon the image of particles as tiny beads. Instead, imagine space as permeated by a collection of invisible, interpenetrating substances, each with its own properties. These are not substances you can scoop or bottle, but continuous entities, more like fluid systems than solid objects. Each field has a value at every point in space and time, and those values can change, ripple, and interact. A particle in this framework is not a thing added to space. It is a localized excitation of a field. An electron is what the electron field looks like when it is excited in a particular way. A photon is an excitation of the electromagnetic field. A quark is an excitation of a quark field inseparable from the gluon field that binds it. When a particle is created, nothing fundamentally new is introduced into space. The field changes its state. When a particle is destroyed, the field does not vanish. It relaxes back toward its ground configuration. The ocean analogy captures this relationship with surprising precision. Think of the ocean as the field. Waves are particles. You can count waves. You can track their energy. You can watch them collide and interfere. But no matter how dramatic the wave, it is never separate from the water. When a wave dissipates, the ocean remains. Asking where the wave went misses the point. It was always a pattern in the water, not an object floating on top of it. Virtual particles fit naturally into this picture. They are not tiny objects popping into and out of existence like fireflies. They are brief, constrained fluctuations of fields during interactions. In the ocean metaphor, they resemble transient ripples or bubbles that appear during a disturbance and vanish almost immediately. They cannot be isolated or observed directly, but their effects accumulate and can be measured. They are bookkeeping devices in calculations, but they reflect real field activity. Once this perspective is adopted, the vacuum becomes conceptually simple, though mathematically subtle. The vacuum is not nothing. It is the state in which all fields are in their lowest energy configuration. That configuration is not featureless. It contains fluctuations, correlations, and structure dictated by the equations of the fields themselves. Remove all particles from a region, and the fields do not leave. They remain present, defining the rules of interaction and the baseline energy of space. This is what is meant by the ubiquity of fields. They exist everywhere without exception. There is no region of the universe, not between galaxies, not inside atoms, not near black holes where the fundamental fields are absent. Their values may vary. Their excitations may be suppressed or enhanced. But their existence is not optional. This idea resolves several puzzles at once. It explains why forces have finite propagation speeds, disturbances travel through fields. It explains why particles can be created and destroyed. They are excitations, not indestructible objects. It explains why empty space can exert pressure, shift energy levels, and influence motion. The fields are still there, even when particles are not. It also forces a reconsideration of what it means for something to be real. In the particle-centric view, reality consisted of objects. Fields were convenient abstractions. In the field-centric view, reality consists of continuous entities, whose excitations we perceive as particles. Objects are no longer fundamental, patterns are. This reversal can feel unsettling because it undermines a deeply ingrained intuition. We are used to thinking that things exist first and relationships come second. Quantum field theory insists on the opposite. The relational structure of fields comes first. What we call things emerge from that structure. The legacy of Faraday is visible everywhere in this framework. His insistence that space itself could carry physical properties laid the conceptual groundwork for a universe filled not with emptiness, but with interacting fields. What he glimpsed experimentally, modern physics formalized mathematically. Space is not an inert container. It is an active participant. When you press your hand against a table, you are not encountering a wall of solid particles. You are encountering the electromagnetic field resisting changes in its configuration. When light travels across interstellar space, it is not moving through nothing. It is a self-propagating excitation of a field that exists everywhere along its path. When particles appear in detectors, they are not arrivals from elsewhere. They are local manifestations of fields responding to interactions. Seen this way, the universe is not built from matter placed inside space. It is built from fields whose excitations give rise to everything we observe. Space is saturated with structure even where it appears empty, and the distinction between something and nothing becomes a matter of excitation, not existence. By the time quantum field theory is fully embraced, the language of particles becomes almost secondary. It remains useful, practical, and often intuitive, but it is no longer fundamental. The deeper description speaks in terms of fields, symmetries, and interactions that fill all of space-time. This is the conceptual shift at the heart of modern physics. Once it is made, the idea of a truly empty universe becomes difficult to sustain. There may be regions with no particles, no radiation, no matter in the classical sense, but there is no place where the fields vanish. The vacuum is not an absence. It is a presence, structured, constrained, and everywhere. And with that realization, the stage metaphor finally collapses. Space is not a backdrop waiting for actors. It is the medium from which the actors themselves arise. At first glance, the uncertainty principle sounds like a statement about human limitation. It is often introduced as if nature were clear and definite, but our instruments were clumsy, our measurements imprecise, our hands too rough to grasp the microscopic world. This interpretation is comforting because it preserves the idea that reality itself is well defined, even if we cannot fully access it. But this interpretation is wrong. What Werner Heisenberg uncovered was not a technical inconvenience. It was a statement about how nature itself is built. The uncertainty principle is not a problem of observation. It is a structural rule of reality. In classical physics, there is no obstacle in principle to knowing everything at once. If you know the position of a particle and the forces acting on it, you can calculate its momentum, its energy, and its future trajectory with arbitrary precision. The world is deterministic and well-defined at every instant. Uncertainty enters only through ignorance. Measure better, and the fog lifts. Quantum physics rejects this picture at its foundation. Certain pairs of physical quantities are not simultaneously well-defined. Position and momentum are the most famous example, but they are not the most important for understanding the vacuum. The deeper pair is energy and time. This is where the emptiness of space becomes restless. The uncertainty principle relating position and momentum can be written schematically as delta x times delta p is greater than or equal to h bar over 2. No matter how perfect your apparatus, the product of the uncertainty in position and the uncertainty in momentum cannot be reduced below this limit. This is not because measurement disturbs the system, but because the system does not possess sharp values for both quantities at once. The wave-like nature of quantum states makes this unavoidable. The energy-time uncertainty relation is subtler because time in quantum mechanics is not an operator in the same sense as position or momentum, and yet the principle is no less real. It can be expressed as delta E times delta T is greater than or equal to h bar over 2. This relation does not mean that energy is poorly conserved. nor does it imply that time itself fluctuates randomly. Instead, it states that over very short timescales, the energy of a system cannot be sharply defined. The shorter the time interval over which you examine a system, the larger the range of energy fluctuations that are allowed. This single statement dismantles the classical idea of a quiet vacuum. In classical thinking, the vacuum is defined as the state of lowest energy, and that lowest energy can be exactly zero. A system at rest stays at rest. Nothing happens unless something disturbs it. But in quantum theory, a system confined to a finite region of space or time cannot have both perfectly defined energy and perfectly defined temporal behavior. If a field were forced to have exactly zero energy at every instant, it would violate the uncertainty principle. Such a state is forbidden. As a result, quantum fields are never allowed to be perfectly still. Even in their lowest energy configuration, they must fluctuate. These fluctuations are not optional features or temporary glitches. They are demanded by the mathematics of the theory. The vacuum is restless because absolute stillness is incompatible with quantum reality. To see why, consider a single quantum harmonic oscillator, the simplest possible quantum system. In classical physics, its lowest energy state corresponds to zero motion. In quantum mechanics, its lowest energy state still carries energy equal to half omega. This is the zero-point energy. The oscillator is not vibrating in a classical sense, but its quantum state has an irreducible spread in position and momentum. Remove that energy and the uncertainty principle would be violated. Quantum fields can be thought of as an infinite collection of such oscillators, one for each mode of vibration at each point in space. Each mode contributes its own zero-point energy. Even when no particles are present, even when no excitations are deliberately introduced, the fields retain this residual energy. The vacuum is not empty. It is the sum of all these unavoidable fluctuations. This is why the phrase, borrowing energy from nothing, is often used, though it must be handled carefully. The vacuum does not loan energy like a bank, and energy conservation is not casually violated. What the uncertainty principle allows is temporary indeterminacy. Over very short timescales, energy need not be sharply defined as long as the system returns to an allowed state quickly enough. The bookkeeping works out precisely, even if the intuitive picture feels strange. Within this framework, the idea of virtual particles emerges naturally. When fields fluctuate, certain patterns resemble the brief appearance of particle-antiparticle pairs. These pairs are not real particles, in the sense that they cannot be directly detected as free entities. They do not persist, and they do not violate conservation laws. They are transient field excitations that exist only within the limits allowed by uncertainty. A particle-antiparticle pair may momentarily appear, exist for an extremely short time, and then annihilate, returning the field to its ground state. This process does not require external energy input because the energy involved is not sharply defined during the brief interval of existence. The shorter the lifetime, the larger the allowed energy fluctuation. These are not speculative ideas. They are calculational tools that produce extraordinarily accurate predictions confirmed by experiments to many decimal places. It is important to stress that virtual particles are not tiny objects popping in and out of existence like sparks in a void. That image is a metaphor, not a literal description. What is truly happening is that quantum fields fluctuate, and when interactions are calculated, these fluctuations can be represented mathematically as intermediate particle-like states. The language of particles is convenient, but the underlying reality remains field-based. The consequence for the vacuum is unavoidable. If quantum fields exist everywhere, and if quantum fields cannot be perfectly still, then the vacuum must contain energy. Not optional energy, not hidden energy. Necessary energy. This is zero-point energy, and it is present even in the absence of matter, radiation, or thermal motion. This energy does not normally announce itself dramatically. It does not heat space to extreme temperatures or cause spontaneous explosions. Its effects are subtle, often cancelling out when symmetries are present, but it is not irrelevant. Under the right conditions, it becomes observable. Shifts in atomic energy levels, tiny forces between closely spaced objects, and even the evaporation of black holes, all trace back to vacuum fluctuations. These phenomena are not added by hand. They fall out of the theory once the uncertainty principle is taken seriously. The deeper implication is philosophical as well as physical. Classical physics allowed the concept of absolute nothingness as a meaningful state of the world. Quantum physics forbids it. A universe governed by uncertainty cannot sit perfectly still. The lowest energy state is not a frozen void, but a dynamic baseline from which all structure emerges. This baseline is not chaos. The fluctuations are constrained, structured, and governed by precise laws. The vacuum is not a turbulent mess, but a tightly regulated system whose behavior can be calculated and tested. The uncertainty principle does not destroy predictability, it reshapes it. Instead of predicting exact trajectories, quantum theory predicts probabilities and correlations with astonishing accuracy. Once this is understood, the restlessness of empty space is no longer mysterious. It is inevitable. A vacuum without energy would violate the uncertainty principle. A field without fluctuations would contradict the mathematical structure of quantum mechanics. The dance of nothingness is not an add-on to reality. It is the foundation upon which everything else is built. Every particle you observe, every force you measure, every structure that persists in the universe exists on top of this fluctuating background. Matter is not placed into a static void. It condenses out of a restless ground state. Even stability itself arises from motion constrained by rules. The uncertainty principle does not merely limit knowledge. It enforces activity. It ensures that the vacuum cannot collapse into silence. It guarantees that even nothing must move. And so the paradox resolves itself. The vacuum has energy not because something is hiding in it, but because quantum reality cannot do otherwise. To exist at all, fields must fluctuate. To fluctuate, they must carry energy. And from that unavoidable energy, everything else ultimately follows. Up to this point, the idea that empty space carries energy and structure may still sound uncomfortably abstract. Fields that fluctuate, virtual particles that appear and disappear, zero-point energy that cannot be removed. All of this could be dismissed as clever mathematics, a formal language physicists use to make calculations work. History is full of beautiful theories that turned out to be wrong. So the crucial question becomes unavoidable. Does quantum emptiness do anything that can be measured, or is it merely a philosophical reinterpretation of equations? Modern physics gives a clear answer. The quantum vacuum is not an interpretation layered on top of experiments. It is something experiments are forced to confront. When physicists isolate matter carefully enough, remove thermal noise, suppress classical forces, and push instruments to extreme precision, nothing begins to act. It pushes, it shifts, it polarizes. The vacuum leaves fingerprints on real macroscopic objects, and it does so in ways that no classical explanation can reproduce. The first and most famous of these fingerprints is the Casimir effect. In 1948, Hendrik Casimir proposed a thought experiment that sounded almost absurd. Take two uncharged, perfectly conducting metal plates, place them extremely close together on the order of micrometers or less inside a vacuum. No electric fields applied. No magnetic fields. No thermal gradients. Classical physics predicts nothing interesting should happen. Two neutral objects in empty space should simply remain where they are. But quantum field theory predicted something startling. The plates should attract each other. The reasoning was subtle but precise. The electromagnetic field exists everywhere, even in a vacuum, and it fluctuates. However, not all fluctuations are allowed in all regions. Between two closely spaced metal plates, only electromagnetic modes with wavelengths that fit between the plates can exist. Longer wavelengths are excluded. Outside the plates, by contrast, the full spectrum of vacuum fluctuations remains available. The result is an imbalance. There are more allowed vacuum modes outside the plates than inside. That imbalance translates into a difference in radiation pressure, pushing the plates together. Nothing classical is pulling them. No charges are involved, no external field is applied. The force arises purely from the modification of vacuum fluctuations by boundary conditions. In other words, by changing the geometry of empty space, you change how strongly it pushes. For years, the Casimir effect remained difficult to test experimentally. The forces involved are extremely small, and separating them from electrostatic contamination is notoriously challenging. But by the late 20th century, advances in precision measurement made clean experiments possible. The attraction was observed. Its strength matched quantum predictions with remarkable accuracy. Today, the Casimir effect is not controversial. It is measured routinely in nanotechnology laboratories and even becomes relevant in the design of micro-electromechanical systems, where tiny components can stick together due to vacuum forces. This was a turning point. The vacuum was no longer a passive background. It was exerting a measurable force on metal plates large enough to see under a microscope. Nothing was doing work. Even more striking is that the Casimir effect is not unique. It is simply the most geometrically intuitive example of a broader phenomenon. Vacuum fluctuations alter the behavior of matter. Decades before Casimir's prediction was experimentally confirmed, another clue had already appeared inside the atom. In the late 1940s, precise measurements of the hydrogen atom revealed a discrepancy. According to the Dirac equation, certain energy levels in hydrogen should be exactly degenerate, identical in energy. But experiments showed a tiny splitting. The levels were not where theory said they should be. This discrepancy became known as the Lamb shift, named after Willis Lamb, who measured it in 1947. The shift was minuscule but unmistakable. Something was nudging the electron's energy levels. Classical physics had no answer. Even early quantum mechanics without fields struggled to account for the effect. The solution emerged only when quantum electrodynamics was fully developed. The electron is not moving through empty space. It is embedded in a fluctuating electromagnetic vacuum. Those fluctuations interact with the electron, slightly modifying the effective electric potential it experiences. The electron is, in a sense, constantly jostled by vacuum activity. This interaction shifts the electron's energy levels by a tiny but measurable amount. The Lamb shift is not an artifact of imperfect measurement. It is a correction demanded by quantum field theory, and its calculated value matches experimental results to extraordinary precision. This was one of the earliest and most decisive confirmations that vacuum fluctuations are physically real. The vacuum was not just influencing macroscopic metal plates, it was altering the internal structure of atoms themselves. At this point, the pattern becomes clear. When matter is isolated well enough, the vacuum does not disappear. It interacts. As experimental techniques advanced into the 21st century, physicists began probing the vacuum in even more direct ways. One particularly elegant line of investigation involved asking whether the vacuum could affect light itself, not through matter, but directly. Between 2015 and 2017, experiments led by Alfred Leitenstorfer used ultra-fast laser pulses to probe vacuum fluctuations on extremely short timescales. The idea was conceptually simple, but technically demanding. Fire an intense femtosecond-scale laser pulse through a region of vacuum. If the vacuum were truly inert, the light should propagate exactly as classical electromagnetism predicts. But if the vacuum fluctuates, then under extreme conditions, those fluctuations should slightly modify how light moves through it. The experiments looked for tiny changes in the polarization of light, subtle rotations or distortions that would indicate interaction with vacuum fluctuations. What they observed was consistent with quantum predictions. The vacuum behaved not as an empty corridor, but as a medium with dynamic properties. Light was not traveling through nothing. It was interacting with the lowest energy state of the electromagnetic field. A useful metaphor here is traffic. In classical physics, light in vacuum travels through an empty highway. In quantum physics, the highway is never completely empty. There is background activity, fleeting, constrained, but real, and under the right conditions. That activity affects how signals propagate. The vacuum is not opaque, but it is not entirely transparent either. Its structure can be felt. These experiments are important not because they are exotic, but because they are conservative. They do not rely on speculative physics beyond the standard model. They do not invoke untested ideas. They confirm predictions made decades earlier by quantum field theory using well-understood principles. The vacuum fluctuations inferred from uncertainty relations and field quantization are not mathematical artifacts. They are part of measurable reality. Taken together, the Casimir effect, the Lamb shift and ultra-fast laser experiments form a coherent picture. The quantum vacuum exerts forces. It shifts energy levels. It modifies the propagation of light. These effects are small, but they are precise. They scale exactly as theory predicts. They vanish when conditions remove the relevant fluctuations, and they cannot be explained by any classical model of empty space. This matters deeply for cosmology and fundamental physics. It means that empty space has physical properties that must be included in any complete description of the universe. You cannot write down equations of motion for matter alone and treat the vacuum as irrelevant. The vacuum participates. It contributes energy pressure and interaction effects. It also forces a re-evaluation of what experimental evidence means in modern physics. We are not talking about dramatic explosions or glowing vacuums. We are talking about shifts measured in parts per billion forces, detectable only at nanometer scales, and polarization changes requiring femtosecond timing. Reality at its deepest level does not announce itself loudly. It reveals itself through consistency. Perhaps the most important lesson of these experiments is not any single effect, but their inevitability. Once quantum fields exist everywhere, once uncertainty forbids perfect stillness, these phenomena are not optional. They must occur. The vacuum cannot be turned off. It cannot be fully isolated. It is always present, always interacting, even when everything else has been removed. This is why the idea that vacuum energy is just philosophy fails. Philosophy does not pull metal plates together. Philosophy does not shift atomic spectra. Philosophy does not rotate the polarization of light. The quantum vacuum does. By the time these experiments are understood together, the picture of empty space as a passive void becomes untenable. The vacuum is not a background. It is a physical system with measurable consequences. Matter does not merely exist in space. It exists with space, interacting continuously with the fields that define what space is allowed to be. And once that point is accepted, a much larger question begins to loom. If vacuum energy is real, measurable, and unavoidable, then what role does it play on the largest scales of the universe itself? Part 5. The Standard Model and the Grand Equation. By the time physics reaches the scale of quantum fields, the familiar organizing tools of everyday science begin to fail. The periodic table, with its neat rows of 118 elements, feels comprehensive, only because it describes chemistry, not reality, at its deepest level. At the foundation of modern physics, matter is no longer categorized by atoms and molecules, but by something far more abstract and far more powerful fields. The Standard Model is the framework that gathers these fields into a single coherent picture. It is not a theory of objects. It is a theory of what space itself is allowed to contain and how it is allowed to behave. And the periodic table is replaced by a new inventory. Instead of elements, the universe is built from a small set of matter fields and force fields. There are 12 matter fields, 6 quark fields, and 6 lepton fields. Quarks come in pairs across 3 generations, forming the building blocks of protons, neutrons, and all atomic nuclei. Leptons include the electron and its heavier cousins, along with neutrinos that barely interact at all. These fields do not sit inside space, like ingredients in a container. They permeate space. At every point in the universe, each of these fields exists, even if it is not excited into a particle. Alongside the matter fields are the force fields. There are 4 of them in the Standard Model framework: the electromagnetic field, the weak nuclear field, the strong nuclear field, and the Higgs field. Gravity conspicuously is not included, a fact that hints at deeper incompleteness, but does not diminish the model's accuracy within its domain. Each force field governs a different aspect of how matter fields interact, bind, transform, and persist. What makes the Standard Model remarkable is not merely that it lists these fields, but that it unifies them mathematically in a single object, the Lagrangian. At first glance, the Standard Model Lagrangian looks intimidating, a dense expression filled with symbols, indices, and coupling constants. But conceptually, it is something very simple. It is a compact instruction manual for the universe. Given this equation, one can derive all known non-gravitational interactions of elementary particles. It tells each field how to move, how to interact with other fields, and how to respond to the structure of space-time. The Lagrangian is not a mystical formula. It is a bookkeeping device that encodes symmetry. Every term in it is constrained by principles such as gauge, invariance, and locality. Nothing is arbitrary. Remove a term, and the theory breaks. Add an unmotivated term, and predictions fail. The fact that this single expression has survived decades of experimental testing is one of the quiet triumphs of modern science. Within this equation, different sectors play distinct roles. The electromagnetic part descends from Maxwell's equations, describing how the electromagnetic field propagates and interacts with charged matter. It governs light chemistry, electricity, and magnetism, the forces most familiar to daily life. In the language of fields, it describes how the electromagnetic field couples to charged matter fields, allowing excitations to exchange energy and momentum. The matter sector is encoded through Dirac-type terms. These describe fermionic fields, quarks, and leptons, and how they move through spacetime. These terms capture the quantum behavior of matter, including spin and relativistic effects. They ensure that electrons behave like electrons, and quarks behave like quarks, with precisely the properties observed in experiments. Without these terms, matter would not be stable in any recognizable sense. Then there is the Higgs sector, the most conceptually counterintuitive part of the Standard Model. The Higgs field does not describe a force in the usual sense. It does not pull objects together or push them apart. Instead, it reshapes the vacuum itself. The Higgs field has a non-zero value, even in empty space. This means the vacuum is not symmetric. It is filled with a background field that interacts with certain matter fields continuously. This interaction is what we perceive as mass. In the Standard Model, mass is not an intrinsic property carried by particles like a label. It is an effect. Particles acquire mass through their interaction with the Higgs field. The stronger the interaction, the heavier the particle. Fields that interact weakly with the Higgs field correspond to light particles. Fields that interact strongly correspond to heavy ones. Fields that do not interact at all remain massless. An analogy often used is that of motion through a medium. not because the Higgs field is a literal substance, but because it captures the idea of resistance. A particle moving through the Higgs field experiences something like drag, not in the sense of slowing down in time, but in the sense that energy is required to change its state of motion. That resistance manifests as inertia. Mass in this view is not a thing particles have. It is a measure of how strongly they couple to a background field that fills all of space. This has profound consequences. If the Higgs field did not exist, or if its vacuum value were zero, all particles that currently have mass would become massless. Electrons would move at the speed of light. Quarks would do the same. Atoms could not form because massless electrons cannot bind to nuclei in stable orbits. Chemistry would collapse. Structures larger than radiation would not exist. The universe as we know it would dissolve into a sea of ultra-relativistic fields. The Higgs field is not a decorative addition. It is a structural necessity for a universe with stable matter. The discovery of the Higgs boson in 2012 was not merely the detection of a new particle. It was confirmation that this background field is real, that empty space is permeated by something that gives matter its weight. What makes the Standard Model extraordinary is the way all these components fit together. The matter fields, the force fields, and the Higgs field are not independent modules. They are interlocked by symmetry principles. Gauge symmetries dictate how fields transform and interact. Break those symmetries incorrectly, and the theory becomes inconsistent. Preserve them correctly, and the structure of interactions emerges naturally. From this perspective, the Standard Model is not a catalogue of particles. It is a map of allowed field interactions in spacetime. Particles appear as localized excitations, because that is how fields express energy when disturbed. The vacuum is not empty, because the Higgs field occupies it. Forces propagate, because gauge fields fluctuate. Matter persists, because fermionic fields obey quantum rules that prevent collapse. Seen as a whole, the Standard Model offers a unified portrait of reality below the scale of gravity. It explains why forces have the strengths they do, why particles have the masses they have, and why interactions obey precise patterns. It does so not by postulating solid building blocks, but by describing a web of fields whose behavior is constrained by symmetry and quantum principles. This picture completes the conceptual shift that began with Faraday and matured through quantum theory. The universe is not built from objects floating in space. It is built from fields that define what space can do. Empty space is not the absence of structure. It is the ground state of a highly organized system. And matter is not something added to that system. It is what the system does when it is excited. The Standard Model is often described as incomplete, and that is true. It does not include gravity. It does not explain dark matter or dark energy. It does not tell us why parameters take the values they do. But incompleteness does not diminish its achievement. Within its domain, it is one of the most successful scientific frameworks ever constructed. In a single equation, it encodes the behavior of all known non-gravitational phenomena. It transforms the vacuum from a passive void into an active participant, and it shows with mathematical precision that the universe is not made of things, but of fields. Fields whose quiet background presence makes the existence of everything else possible. Among all objects predicted by modern physics, black holes seem the most absolute. They are regions where gravity overwhelms every other interaction, where escape becomes impossible, where classical intuition finally breaks. For decades after their theoretical discovery, black holes were treated as the ultimate sinks of the universe. Whatever crossed the event horizon was lost forever, and the black hole itself was eternal, changing only by swallowing more matter, or merging with others. In this classical picture, black holes were simple. They had mass, charge, and spin, and nothing else mattered. Quantum physics quietly dismantled that simplicity. When vacuum energy is taken seriously, black holes cease to be inert endpoints. They become laboratories where the deepest principles of quantum fields, space-time, and thermodynamics collide. At the heart of this collision lies one of the most unsettling discoveries of 20th century physics. Black holes are not completely black. They glow. This realization is inseparable from the structure of the quantum vacuum. In quantum field theory, empty space is never truly empty. Fields fluctuate everywhere, and these fluctuations are unavoidable. Normally, such fluctuations remain hidden, averaging out in ways that leave no macroscopic trace. But near a black hole, space-time itself is violently distorted. The presence of an event horizon, a boundary beyond which no signal can return, changes the bookkeeping of quantum fluctuations in a profound way. To understand what happens, consider how quantum fields behave near the event horizon. In ordinary space, vacuum fluctuations constantly produce correlated pairs of field excitations. In particle language, these are often described as particle-antiparticle pairs. They are not real long-lived particles, but fleeting excitations that annihilate almost immediately, leaving no trace. Their existence is allowed by the energy-time uncertainty principle, and their effects normally cancel. Near an event horizon, however, the geometry of space-time interferes with this cancellation. One member of a fluctuation pair may find itself just outside the horizon while its partner appears just inside. The event horizon prevents them from reuniting. From the perspective of an observer far away, something remarkable happens. The particle outside escapes to infinity as real radiation, while its partner is lost to the black hole. Energy conservation is not violated, but it is enforced in a subtle way. The particle that falls into the black hole carries negative energy relative to an observer at infinity. The black hole's total mass decreases by precisely the amount of energy carried away by the escaping particle. This process is known as Hawking radiation, first derived in the 1970s by Stephen Hawking. It was not guessed from intuition. It emerged from a careful calculation of quantum fields in curved spacetime, and its implications were shocking. A black hole once thought eternal slowly loses mass. It evaporates. The temperature of this radiation depends inversely on the black hole's mass. Stellar mass black holes are extremely cold, far colder than the cosmic microwave background, and their radiation is negligible on human timescales. But the principle is universal. No black hole is perfectly stable. Given enough time, even the most massive black hole will radiate away all of its mass. This result establishes something extraordinary. The quantum vacuum can extract energy from a macroscopic object whose gravity is strong enough to trap light itself. The vacuum is not merely a passive background. It participates actively in the evolution of space-time. What is being radiated is not material that was stored inside the black hole. It is energy drawn from the gravitational field mediated by quantum fluctuations near the horizon. The black hole loses mass not because something escapes from within, but because the vacuum outside reorganizes itself in a way that carries energy away. This turns the classical picture inside out. Instead of black holes being perfect absorbers, they become thermodynamic objects with temperature, entropy, and finite lifetimes. The vacuum, once thought irrelevant at large scales, becomes the agent of their slow demise. The evaporation process also forces black holes into the framework of thermodynamics. The area of the event horizon behaves like entropy. The surface gravity corresponds to temperature. These relationships are not analogies. They are exact. A black hole obeys laws formally identical to the laws of thermodynamics, and vacuum energy is central to that correspondence. This raises an immediate and disturbing question. If a black hole evaporates completely, what happens to the information about everything that fell into it? In classical general relativity information, crossing the event horizon is gone forever. In quantum mechanics, information is not supposed to be destroyed. The equations that govern quantum evolution are reversible. They preserve information even if it becomes scrambled beyond practical recovery. Hawking radiation, however, appears thermal. it seems to carry no information about the internal state of the black hole. If the black hole disappears and only featureless radiation remains, information appears to be lost. This tension is known as the black hole information paradox. It is not a philosophical puzzle. It is a direct conflict between the principles of quantum mechanics and the predictions of semi-classical gravity. Vacuum energy sits at the center of this conflict. Hawking radiation originates from vacuum fluctuations near the horizon. If those fluctuations produce radiation that is truly thermal and uncorrelated with the black hole's interior, then quantum unitarity is violated. If information is preserved, then the structure of the vacuum near the horizon must be far subtler than originally thought. Over the past decades, many proposed resolutions have emerged subtle correlations in the radiation holographic descriptions of space-time quantum gravity effects that modify the horizon itself. None of these ideas can be fully tested yet, but all of them share a common lesson. The vacuum is not a trivial stage on which gravity acts. It is an active, information-bearing component of reality. Even without resolving the paradox, Hawking radiation already teaches something profound. It shows that vacuum energy is not confined to microscopic effects. Under extreme gravitational conditions, it reshapes the fate of the largest objects in the universe. The same vacuum fluctuations that shift atomic energy levels and pull metal plates together also determine the lifespan of black holes. This unity of scale is one of the most striking features of modern physics. The quantum vacuum does not care whether it is interacting with an electron or a black hole. The principles are the same. Fields fluctuate, boundaries matter, energy flows according to precise rules. In this sense, black holes are not exceptions to the laws of physics. They are amplifiers. They magnify the consequences of vacuum structure until they become unavoidable. Where gravity is weak, vacuum energy whispers. Where gravity is strong, it speaks loudly. The evaporation of black holes also undermines the idea of permanence. Even the darkest, densest objects in the cosmos are temporary configurations. They form, evolve, and dissolve, guided not only by gravity, but by quantum fields that fill space. The universe has no final sinks, only transformations. Seen from this perspective, vacuum energy is not a small correction to an otherwise classical universe. It is a foundational element. It links quantum uncertainty to cosmic evolution. It connects the smallest fluctuations to the ultimate fate of massive objects, and it forces physicists to confront the limits of current theories. Black holes, once imagined as silent prisons of matter, become dynamic participants in a universe where emptiness is active. They radiate because the vacuum will not remain still. They evaporate because uncertainty cannot be confined indefinitely. And they challenge our understanding of information because the vacuum itself may carry more structure than we have yet learned to describe. In the end, black holes reveal the vacuum for what it truly is. Not the absence of everything, but a restless, energetic foundation capable of shaping even the most extreme corners of reality. If modern physics were a perfectly coherent story, the quantum vacuum would have already revealed its true weight to the cosmos. By now, after everything quantum field theory has taught us about zero-point energy fluctuating fields and unavoidable vacuum activity, the universe should look dramatically different. In fact, according to our best calculations, it should not look like a universe at all. This is where the story reaches its most unsettling point, because here, theory and observation collide with a violence unmatched anywhere else in science. Quantum field theory insists on a simple but brutal statement. Every quantum field contributes energy to empty space. Not optional energy, not adjustable energy, but mandatory zero-point energy. Each mode of each field behaves like a quantum oscillator, and each oscillator carries a minimum energy that cannot be removed. When physicists do what physicists always do, add everything up, the result is staggering. Summing the zero-point energy of all known quantum fields, even with conservative cutoffs, yields a vacuum energy density on the order of 10 to the power of 113 joules per cubic meter. This number is not a typo. It is not a fringe estimate. It is the natural outcome of applying quantum field theory as we understand it. To appreciate the scale of this value, it helps to strip it of abstraction. A joule is a modest unit of energy. A few joules can lift an apple. 100 joules can power a light bulb briefly. But 10 to the power of 113 joules packed into a single cubic meter is beyond anything encountered in astrophysics, nuclear physics, or particle physics. It is an energy density so enormous that if it gravitated the way energy is supposed to gravitate, space-time itself would be violently distorted. General relativity is unambiguous on this point. Energy curves space-time, pressure curves space-time. Vacuum energy in particular acts as a source of gravitational repulsion. Put enough of it into the equations, and space-time does not merely bend it, accelerates outward. With a vacuum energy density of the magnitude predicted by quantum field theory, the universe would either explode apart at unimaginable speed or collapse almost instantly, depending on the sign of the contribution. Either way, galaxies, stars, atoms, and observers would never form. And yet here we are. Astronomical observations tell a very different story. In the late 1990s, independent teams studying distant Type Ia supernovae discovered that the expansion of the universe is accelerating. This acceleration is not driven by matter or radiation, but by something with negative pressure, something that behaves like energy inherent to space itself. This component is now called dark energy, and in the simplest interpretation, it is mathematically equivalent to a cosmological constant denoted by L. The measured value of this energy density is astonishingly small, roughly 10 to the minus 9 joules per cubic meter. Compared to everyday energy densities, it is barely there. Compared to the quantum field theory prediction, it is effectively zero. The ratio between the theoretical value and the observed value is about 10 to the power of 120, 120 orders of magnitude. No other discrepancy in the history of physics comes close. This is why the cosmological constant problem is often described as the worst theoretical prediction ever made. Not because the mathematics is sloppy, but because the mathematics is internally consistent. Quantum field theory is spectacularly successful in every laboratory test ever performed. General relativity is spectacularly successful in describing gravity across cosmic scales. And yet, when the two are combined in the most straightforward way, the result is catastrophically wrong. This is not a minor mismatch. It is not a missing factor of 2. It is not a sign error. It is a fundamental crisis. If quantum field theory is correct about vacuum energy, then empty space should dominate the universe completely. Matter would be irrelevant. Structure would be impossible. Time itself would unfold too violently, or not at all. Conversely, if cosmological observations are correct, and they are confirmed by multiple independent probes, including the cosmic microwave background and large-scale structure, then something must be suppressing the vacuum energy by an extraordinary degree. The question is not whether there is a discrepancy. The question is how nature hides it so perfectly. One might imagine simply subtracting the vacuum energy by hand, declaring it unphysical. But this approach fails immediately. Vacuum energy is not a bookkeeping artifact. It produces measurable effects, as seen in the Casimir effect, the Lamb shift, and Hawking radiation. You cannot erase it in one context without destroying agreement in others. The vacuum clearly has energy. The problem is not its existence, but its gravitational impact. This is where the cosmological constant problem reveals its true depth. Gravity responds to absolute energy, not just differences. In quantum field theory, it is often only energy differences that matter, so large constant offsets can be ignored. In gravity, there is no such luxury. The vacuum energy gravitates, whether we like it or not. Historically, the cosmological constant was introduced by Albert Einstein as a mathematical device to allow for a static universe. After the discovery of cosmic expansion, Einstein reportedly regarded it as his greatest mistake. Ironically, the constant returned decades later, not as an arbitrary addition, but as an observed feature of the universe. The modern problem is not that Ley exists, but that its value is absurdly small compared to what quantum theory predicts. Why is it so small? Why not exactly zero? Why not enormous? Why just barely enough to accelerate cosmic expansion, slowly allowing galaxies and stars to form over billions of years before being pulled apart? These questions strike at the heart of our understanding of naturalness in physics. Normally, when a quantity can receive large contributions from known processes, its observed value is expected to be comparably large unless protected by a symmetry. The cosmological constant appears unprotected. Every known field contributes. Every quantum fluctuation adds to the total. And yet the sum is almost perfectly cancelled. This suggests one of three unsettling possibilities. The first is that there exists an unknown symmetry or mechanism that enforces near-perfect cancellation. Supersymmetry is often mentioned in this context. In a supersymmetric universe, each bosonic field has a fermionic partner, and their vacuum energy contributions cancel exactly. But supersymmetry, if it exists, must be broken at energies far above what we observe, leaving a residual vacuum energy that is still many orders of magnitude too large. Supersymmetry helps, but it does not solve the problem completely. The second possibility is that our understanding of gravity is incomplete. Perhaps vacuum energy does not gravitate in the naive way predicted by general relativity. Perhaps space-time responds only to changes in energy, or perhaps some deeper principle cancels vacuum contributions dynamically. This idea motivates modifications of gravity, emergent space-time models, and holographic approaches. None have yet produced a fully convincing solution. The third possibility is the most controversial, that the small value of the cosmological constant is environmental. In a vast multiverse, different regions could have different vacuum energies. Most would expand too fast or collapse too quickly for structure to form. Observers would naturally find themselves only in regions where the vacuum energy is small enough to permit complexity. This anthropic reasoning is uncomfortable for many physicists because it shifts explanation from dynamics to selection, but it remains logically consistent with current evidence. Regardless of which path is correct, the conclusion is unavoidable. The cosmological constant problem exposes a profound mismatch between our deepest theories. It tells us that quantum field theory, as powerful as it is, cannot be the final word when combined with gravity. It tells us that empty space is not just a backdrop, but a dynamical entity whose energy content controls the fate of the universe. In this sense, the problem is not a failure. It is a signpost. It points toward new physics that we do not yet understand. It suggests that the vacuum hides a principle more subtle than anything encountered so far. The universe appears finely balanced on a knife edge between violent expansion and gravitational collapse, and the reason for that balance remains unknown. What makes this problem especially haunting is its silence. The universe does not scream its instability. It expands calmly. Galaxies form, stars burn, life emerges. All of this unfolds in apparent defiance of theoretical expectations. The worst prediction in physics is not loud. It is quietly wrong. And until we understand why the vacuum energy that quantum theory demands does not tear the universe apart, we are forced to admit that our picture of reality is incomplete. in a way that no adjustment of parameters can fix. The cosmological constant problem is not just a numerical embarrassment. It is the clearest signal that something fundamental about the relationship between quantum fields, gravity, and empty space remains deeply hidden. For much of the 20th century, cosmology lived under a quiet assumption: the expansion of the universe discovered by Edwin Hubble was slowing down. Gravity, after all, pulls things together. Galaxies rush apart because of the initial conditions of the Big Bang, but their mutual attraction should gradually decelerate that motion. The question was never whether the expansion would slow, but how much. Everything about matter, radiation, and gravity pointed in the same direction. The universe was expanding, yes, but reluctantly. Then, in 1998, that expectation collapsed. Two independent teams studying distant Type Ia supernovae, stellar explosions used as standard candles, found something deeply unsettling. These supernovae were dimmer than expected, not because of dust, not because of measurement error. The only consistent explanation was that the universe had expanded more than it should have if gravity were slowing it down. The expansion was not decelerating, it was accelerating. The universe was speeding up. This was not a subtle effect. It was a wholesale reversal of intuition. Something was acting against gravity on the largest scales imaginable, pushing space-time itself to expand faster and faster over time. This discovery forced cosmology to confront a new dominant component of the universe: dark energy. Dark energy is not dark because it absorbs light. It is dark because it does not clump, does not radiate, and does not interact with matter in any conventional way. Its presence is inferred only through its gravitational effect, or more precisely, through its repulsive influence on cosmic expansion. Today, dark energy is estimated to make up about 70% of the total energy content of the universe. Ordinary matter, everything from stars to people, accounts for less than 5%. Whatever dark energy is, it dominates the cosmic budget. The simplest way to describe dark energy is to resurrect an old idea: the cosmological constant. Long before supernova observations, Albert Einstein introduced the cosmological constant, denoted L, into his equations of general relativity. His motivation was pragmatic. At the time, the universe was believed to be static. Gravity alone would cause a static universe to collapse, so Einstein added a repulsive term to balance it. When cosmic expansion was discovered, the need for L vanished, and Einstein reportedly regarded its introduction as a mistake. History, however, had other plans. In modern cosmology, the cosmological constant has a clear physical interpretation. It represents a constant energy density associated with space itself. Unlike matter or radiation, whose energy density decreases as the universe expands, a cosmological constant remains unchanged. As space stretches more, vacuum energy appears, and its repulsive gravitational effect grows stronger relative to matter. This naturally leads to accelerated expansion. Mathematically, this fits the supernova data remarkably well. A universe with cold dark matter and a small positive cosmological constant reproduces observations across multiple scales: supernovae, the cosmic microwave background, baryon acoustic oscillations, and large-scale structure. From a purely phenomenological standpoint, L works. It is economical. It is stable. It requires no additional dynamics. But conceptual comfort is another matter entirely. The moment one asks what Li is the problem reopens. In quantum field theory, empty space is not empty. It is filled with zero-point energy from quantum fields. That energy has exactly the right properties to act like a cosmological constant. It is uniform. It does not dilute with expansion. It exerts negative pressure. On paper, vacuum energy and dark energy look identical. And yet, as we have already seen, their magnitudes do not match, not even remotely. If dark energy was simply the vacuum energy predicted by quantum field theory, its density should be enormous enough to tear the universe apart almost instantly. Instead, it is absurdly small, just large enough to accelerate cosmic expansion gently over billions of years. This is the broken link at the heart of modern cosmology. Dark energy behaves like vacuum energy, but refuses to have the value vacuum energy calculations demand. This forces a crucial distinction. In cosmology, dark energy is defined operationally, whatever causes accelerated expansion. Vacuum energy is defined theoretically, the energy of the ground state of quantum fields. They may be related, they may even be the same thing, but current theory cannot explain why they differ by 120 orders of magnitude. Because of this failure, physicists have explored alternatives. One possibility is that dark energy is not constant at all, but dynamical. Instead of a fixed loc, the acceleration could be driven by a new scalar field that evolves slowly over cosmic time. This class of models is often called quintessence. In such scenarios, the energy density changes gradually, potentially explaining why dark energy is small today, without requiring perfect cancellation in the vacuum. Quintessence fields behave differently from vacuum energy. They can vary in space and time. Their equation of state may deviate slightly from that of a cosmological constant. In principle, careful astronomical observations could detect such deviations. So far, however, the data remains stubbornly consistent with a constant value. If quintessence exists, it is extraordinarily subtle. Another line of thought questions gravity itself. Perhaps general relativity responds differently to vacuum energy than to other forms of energy. Perhaps the equations that govern cosmic expansion emerge from deeper principles in which vacuum contributions cancel automatically. These ideas motivate theories of modified gravity and emergent space-time. But like quintessence, they remain speculative. What makes dark energy especially unsettling is not just that it exists, but that it is finely balanced. Its density is small, but not zero. If it were even modestly larger, galaxies would never have formed. If it were zero or negative, cosmic expansion might eventually halt or reverse. The value we observe lies in a narrow window that allows complex structure to exist for billions of years before accelerated expansion dominates. This apparent fine-tuning has led some physicists to consider anthropic explanations. In a multiverse, different regions could have different values of vacuum energy. Most would be inhospitable to structure. Observers would naturally find themselves only in regions where dark energy is small enough to permit stars, planets, and life. This idea is controversial not because it is illogical, but because it shifts explanation away from dynamical laws toward selection effects. Many physicists find this deeply unsatisfying. Yet in the absence of a better mechanism, it remains on the table. The distinction between vacuum energy and dark energy is therefore not semantic. Vacuum energy is a prediction of quantum field theory. Dark energy is an empirical fact of cosmology. Their apparent similarity hides a profound mismatch. One emerges from the mathematics of microscopic fields. The other governs the fate of the entire universe. Bridging that gap is one of the central challenges of theoretical physics. What dark energy ultimately teaches us is humility. The universe is not obligated to align with our theoretical expectations. It accelerates because it does, not because we understand why. Our equations can describe its behavior with exquisite precision, yet fail catastrophically when asked to explain its origin. Dark energy is invisible but not passive. It is the dominant driver of cosmic evolution today. It shapes the future of space-time, determining whether galaxies drift beyond each other's horizons, whether stars fade into isolation, whether the observable universe becomes emptier and colder with time. And yet, despite its influence, dark energy remains the least understood component of the cosmos. It sits at the intersection of quantum theory and gravity, exposing the fault line between them. It behaves like vacuum energy, but refuses to be vacuum energy as we calculate it. It looks simple, but demands explanation beyond simplicity. In this sense, dark energy is not just an ingredient of the universe. It is a message. It tells us that our understanding of empty space is incomplete, that the vacuum still hides principles we have not uncovered, and that the largest scale behavior of the universe is controlled by physics we do not yet know how to describe. The universe accelerates not because it must, but because something unseen tells it to. And until we understand what that something is, dark energy remains the invisible architect of cosmic history. There is a limit to how deeply our familiar concepts of space and time can be trusted. For centuries, geometry felt absolute. Space extended smoothly in all directions. Time flowed uniformly forward, and distances could always be divided into smaller distances without encountering anything fundamentally new. Even Einstein's general relativity, radical as it was, preserved this intuition at its core. Space-time could curve, stretch, and warp, but it remained a smooth continuum, like a fabric that could be bent but never torn. No matter how closely you zoomed in, the fabric was still there. Quantum physics quietly disagreed. When gravity and quantum mechanics are pushed into the same conceptual space, they point to a scale beyond which the very idea of smooth space-time stops making sense. This scale is not chosen arbitrarily. It is constructed from the fundamental constants of nature: the speed of light, Planck's constant, and Newton's gravitational constant. Combine them, and a characteristic length emerges about 10 to the power of -35 meters. This is the Planck length. It is not merely small, it is staggeringly small, many orders of magnitude smaller than a proton, smaller than anything we can probe directly with any conceivable experiment. The Planck length marks the boundary where our current theories lose their authority. Below this scale, space-time cannot be assumed to behave like a smooth geometric arena. The fluctuations demanded by quantum mechanics become so violent that geometry itself ceases to be well-defined. Distances fluctuate, curvature fluctuates. Even the causal order of events becomes ambiguous. The language of here and there, before and after, begins to dissolve. This realization led John Wheeler to propose one of the most evocative images in modern physics: quantum foam. According to this picture, space-time at the Planck scale is not calm or continuous. It is a seething, frothy structure, constantly forming and dissolving microscopic features. Tiny wormholes may briefly connect nearby regions before collapsing. Curvature spikes appear and vanish. The topology of space itself fluctuates as if space-time were boiling at the smallest scales. The term foam is not meant to be literal. There is no fluid bubbling beneath reality. It is a metaphor for instability. In this regime, the quantum uncertainty of the gravitational field becomes unavoidable. Because gravity is geometry, uncertainty in gravity becomes uncertainty in space-time itself. The metric that defines distances and times cannot settle into a single configuration. It fluctuates violently around every possible value allowed by quantum rules. At human scales, these fluctuations are utterly negligible. They average out so completely that space-time appears smooth and classical. Even at the scale of atoms, space-time is effectively flat. But as one approaches the Planck length, the averaging breaks down. The fluctuations no longer cancel, they dominate. This is where the deepest conflict in modern physics becomes unavoidable. General relativity and quantum mechanics are both extraordinarily successful, but they are built on incompatible assumptions. General relativity treats space-time as a continuous manifold, smooth at all scales, governed by deterministic equations. Quantum mechanics treats physical quantities as operators with uncertainty governed by probabilistic rules. When gravity is weak, quantum effects of space-time can be ignored. When quantum effects are strong, gravity can often be ignored. At the Planck scale, neither can be neglected. In that regime, general relativity predicts infinite curvature and singular behavior. Quantum mechanics predicts fluctuations so large that the very notion of a classical geometry collapses. The equations of one theory destroy the assumptions of the other. This is not a technical problem, it is a conceptual fracture. Quantum foam is not a complete theory, it is a signal. It tells us that space-time itself must be described quantum mechanically, not merely as a background on which quantum fields live. It suggests that space-time may not be fundamental, but emergent, a large-scale approximation arising from deeper, non-geometric degrees of freedom. Attempts to resolve this conflict have shaped theoretical physics for decades. Two major approaches illustrate how radically different the solutions might be. In string theory, the fundamental objects are not point-like particles, but extended one-dimensional strings. Their vibrations correspond to different particles, including a massless spin-2 excitation that behaves like a graviton. Crucially, string theory softens interactions at very short distances. Because strings have finite size, they smear out the violent fluctuations that plague point-particle descriptions. In this framework, space-time geometry emerges from the collective behavior of strings and higher-dimensional objects. The Planck scale is no longer a singular boundary, but a regime where new degrees of freedom dominate. Loop quantum gravity takes a different path. It quantizes space-time itself directly. In this approach, space is not continuous, but composed of discrete units, tiny chunks of area and volume connected in a network-like structure. Geometry becomes granular. Distances and areas have minimum possible values. At large scales, this discrete structure approximates smooth space-time. At the Planck scale, the granularity becomes unavoidable. Quantum foam is replaced by a combinatorial structure, whose fluctuations are governed by quantum rules. Despite their differences, both approaches agree on a key point: smooth space-time is not fundamental. It is an emergent description valid only when quantum gravitational effects are suppressed. Below the Planck scale, asking for a precise distance or a definite geometry may be as meaningless as asking for the exact trajectory of an electron inside an atom. This has profound implications for how we think about reality. Space and time, long treated as the stage on which physics unfolds, may themselves be actors or even byproducts of deeper processes. The universe may not be built in space-time. Space-time may be built by the universe. Quantum foam also reframes the idea of nothingness. If space-time itself fluctuates, then the vacuum is not just filled with quantum fields, it is filled with fluctuating geometry. The emptiness beneath everything is not a calm void, but a restless, unstable structure whose average appearance only masquerades as smoothness. This does not mean space-time is literally tearing itself apart at microscopic scales in a way that affects everyday physics. The foam is confined to the Planck regime, sealed off from direct observation by the extreme energies required to probe it. But its existence has indirect consequences. It shapes how black holes encode information. It influences how the early universe may have behaved near the Big Bang. It sets the ultimate limit on localization and measurement. The Planck scale is therefore not just a small distance. It is a conceptual horizon. Beyond it, the categories inherited from classical physics cease to apply. Position, duration, curvature, even dimensionality may lose their conventional meaning. What replaces them is not yet known. What is known is that neither general relativity nor quantum mechanics can be the final story on their own. The violent fluctuations implied by quantum foam are not an embarrassment to be ignored. They are a clue. They tell us that space-time, like matter and energy, must ultimately obey quantum principles, but in a way we do not yet fully understand. In the end, quantum foam represents the last layer of emptiness. Below atoms there are fields. Below fields there is vacuum energy. Below vacuum energy there is geometry itself in flux. The deeper we go, the less emptiness becomes. And at the smallest scales imaginable, even space and time refuse to remain still. At the Planck scale, the universe does not rest on a smooth foundation. It balances on a storm of quantum possibilities, from which the calm geometry of our everyday world slowly emerges. After traveling from atoms to fields, from vacuum energy to cosmic expansion, from black holes to quantum foam, the original intuition we began with can no longer survive intact. The idea that there exists a simple, silent emptiness beneath reality dissolves completely. What we once called empty space turns out to be the most active ingredient in the universe. It is not a void waiting to be filled. It is a physical system in its own right, governed by laws carrying energy, storing information, and shaping everything that can exist within it. Seen from this vantage point, the universe is not built like a machine assembled from solid parts. It is built like a pattern, a hierarchy of excitations layered upon a restless foundation. At the deepest level we can currently describe, reality consists of quantum fields extending everywhere, never switching off, never fully settling into silence. Particles are not objects inserted into space. They are what fields do when they are disturbed. Forces are not mysterious pushes across emptiness. They are interactions between fields that share the same space-time fabric. Even space-time itself, once thought immutable, appears to emerge from deeper quantum structure. When we say that space is full, we do not mean it is crowded with hidden matter. We mean it is occupied by fields whose ground states are active, fluctuating, and constrained by quantum rules. These fluctuations are not noise to be ignored. They give rise to measurable forces, shift atomic energy levels, radiate from black holes, and drive the expansion of the universe. Empty space does not merely host physics, it participates in it. From this perspective, the distinction between matter and space becomes less sharp. Matter is not something that sits inside space like furniture in a room. Matter is a particular way space behaves when its fields are excited in stable, localized patterns. Atoms are standing waves. Molecules are coupled oscillations. Solids are rigid, not because they are packed with substance, but because their underlying fields resist rearrangement. Even mass itself is not a primitive ingredient. It arises from interaction with a background field that fills all of space. This reframing changes how we think about ourselves. Every atom in your body is a configuration of quantum fields. Every chemical bond is an electromagnetic interaction mediated by field excitations. Every nerve impulse is a coordinated flow of charged fields through molecular structures. Even the electrical activity of your brain, the physical substrate of thought, is governed by the same field equations that describe stars and galaxies. There is no sharp boundary where the universe ends and you begin. The same fields that ripple through intergalactic space ripple through you. In this sense, you are not merely in the universe. You are the universe expressing itself locally. There is no separate category of human matter distinct from cosmic matter. There are only fields and their excitations. The difference between a person and a planet is not one of substance, but of pattern, scale, and organization. Both are solutions to the same underlying equations. Understanding this does not diminish individuality. It reframes it. Individuality is not isolation. It is a particular mode of vibration that persists for a time within a much larger dynamical system. You are a long-lived wave pattern, stabilized by interactions maintained by energy flow, embedded in a field-filled universe that never truly rests. This view also alters how we think about nothingness. Nothing is not the absence of being. It is the lowest energy configuration of everything that exists. It is the ground state of all fields, including those we have not yet discovered. It is structured, constrained, and active. The vacuum is not a blank page. It is the paper on which the universe writes itself. And we are still only beginning to read that writing. The story does not end with what we currently know. our most powerful instruments continue to probe deeper. Particle accelerators push energy higher, attempting to reveal whether new symmetries exist that could explain why vacuum energy is so finely balanced. The Large Hadron Collider has already confirmed the existence of the Higgs field, validating the idea that empty space itself determines the properties of matter. Future machines, such as the proposed Future Circular Collider, aim to explore energies where new fields or new principles might emerge. One possibility is supersymmetry, a symmetry that would pair every known field with a partner field, potentially cancelling enormous vacuum contributions and resolving the cosmological constant problem. Another possibility is something more radical, that vacuum energy is regulated by a principle we have not yet imagined, one that reshapes how gravity and quantum fields coexist. Or it may be that space-time itself emerges from quantum information in a way that renders our current notion of vacuum energy incomplete. What is certain is that the vacuum is not a solved problem, it is the frontier. Every major puzzle we face, dark energy, black hole information, quantum gravity, converges on the same question. What is the true nature of empty space? Why does it behave the way it does? Why does it permit a universe rich enough to contain stars, chemistry, and consciousness? These questions are not separate from human experience. They are its precondition. The fact that vacuum energy is small enough to allow galaxies to form stable enough to permit long-lived structures and structured enough to support complexity is not incidental. It is the reason there is something rather than nothing in any meaningful sense. When you look into the night sky and see darkness between the stars, you are not seeing absence. You are seeing the most fundamental layer of reality, a field-filled expanse whose quiet activity makes all light, all matter, and all time possible. The darkness is not empty. It is pregnant with structure. And when you close your eyes and feel your own existence, the weight of your body, the flow of thought, the continuity of awareness, you are experiencing the same underlying reality from within. The same fields that curve space-time around galaxies coordinate the motion of electrons in your cells. The same quantum rules that forbid perfect stillness in the vacuum forbid perfect stillness in you. Nothing stands apart from this framework. Not matter, not life, not mind. In the end, the most radical conclusion of modern cosmology is not that the universe is strange, but that it is continuous. There is no sharp divide between emptiness and substance, between space and thing, between observer and observed. There are only fields interacting, fluctuating, organizing themselves into patterns that persist for a time. Nothingness, as classical thought imagined, it does not exist. What exists instead is a restless foundation, a dynamic ground state from which everything arises and to which everything ultimately returns. When you look into empty space, you are not looking at the absence of reality. You are looking at its source. And when you recognize that source within yourself, you are not diminishing the universe. You are locating yourself precisely where physics says you belong, as a wave in the field, a momentary expression of a cosmos that has never been empty and never will be. Thank you for spending this quiet stretch of time here with me, following these ideas slowly, patiently, all the way from empty space to the deepest structure of reality. If these thoughts brought you even a small sense of calm, or helped the universe feel a little less distant and a little more familiar, then this journey has already meant something to me. Wherever you are listening from, at the end of a long day in a dim room or under a sky filled with stars you cannot see but know are there, I hope your mind can rest now, knowing that even the silence around you is alive with gentle order and that you are never truly separate from it. May your thoughts soften, your breathing slow, and your rest come easily tonight. Sleep well and let the universe keep watch for a while.